Look. 1, 2, 3, 4, 5. 5, 5. 1, 2, 3, 4, 5. Hello, test 1, 2, 1, 2, 1, 2. Test 1, 2, 3, 4. 1, 2, 3, 4. Am I there? 1, 2, 3, 4. Yes, I am. Yes, I am. Alright, stand by. Hello. Oh, there it is. Finally. What the hell happened to my audio? God's truth. Alright, I think we're on. This is VK3EKH. Just bear with me for a tick. Let me go to live camera. Just do this. Okay, we're on live. Finally. Just within 15 seconds to go on air, for some reason I lost audio. I tested it and it worked and then it disappeared. Isn't that just typical? Alright, let me just put my headphones on, make sure that the level on 80 meters is okay. If I can find my headphones. Oh, just last minute problems here. Let me just see if that's working okay. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Very thin, isn't it? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay, I think that will do. Oh, good grief. Good evening is usually how I start off. This is VK3 Echo Kilo Hotel, the official station of the Astronomical Society of Victoria, with the regular Friday night broadcast, with the regular hassles and problems and the usual things that happen, coming to you from the studios of VK3 CSJ in Narre Warren South. And I've just realised I don't have my proper glasses on, but that's okay. And we're broadcasting on the prime frequency of 3541 kilohertz in the 80 metre amateur radio band, and also via the Melbourne television repeater in full HD, VK3 RTV, and also via my two streams, which hopefully will not fall over tonight, courtesy of Telstra or the NBN, one or the other, both perhaps. Actually, it's my fault because of RF getting into the modem, so I can't blame them totally. And anyway, so we're streaming on my Discord channel. So if you haven't got Discord, suggestion is to sign up to Discord, and you can see my my HD stream on Discord. If you go to my qrz.com page, VK3CSJ or VK3EKH, I provide a universal link of sorts that'll get you to the astronomy chat room and also where the digital stream is. I say that all the time because the Discord video stream is far better than the YouTube stream, since there is no delay. Well, microseconds, milliseconds, let's put it. Whereas with YouTube, the video delay can be anything up to 20 seconds. So what you're hearing of me live on 80 meters as such. Otherwise, I am streaming on my YouTube channel. Just go to VK3CSJ in the YouTube search engine and look for the live indication, and you should see me there. I've got a little clock running in the corner there. Actually, it's I should change that to my the other ID, which is more appropriate, and that's my picture-in-picture. Where is it? There it is. So, Astronomical Society Victoria, ASV Radio, VK3EKH. Alright, so we're running about 200 watts on 80 meters using an FTDX 9000D. Apologies if the audio seems to be a little thin, because I haven't quite got the EQ sorted out for this radio, since the icon box, the Pro 3, both Pro 3s are currently out of order. So I'm using the 9000D, which is just a little bit differently set up. But I think it's okay. We have an email address if you wish to send signal reports, both from 80 meters and TV and the streams, to VK3EKH@gmail.com, VK3EKH@gmail.com, and I'll keep an eye open on the inbox as I speak throughout the next hour. Alright, I hope the audio level on YouTube is okay. I can see that I'm clipping into the red on vMix, so hopefully the audio level on YouTube is not distorted in any respect, so I'll just back off the microphone perhaps a tad. Good evening, as they say. Alright, we've got a last, because it's still early in the month, astronomer Tanya Hill's sky notes have come through, although they weren't available for last Friday, so they're here now, and so I shall go through Tamitha's sky notes, as I usually do at the beginning of the month when the notes come through, which will give you a bit of a rundown of what is up in the sky for June. But before I do, I'll do the usual introduction about the ASV for those that aren't aware of ASV's business as such. Let me see if I'll just bring up this one instead, I think. So for those tuning in for the first time, and I can feel the sneeze coming on. It's just a tickle in my nose right now, would you believe it? Excuse me. Alright, I think I got rid of that. The ASV is a non-profit society for people interested in astronomy, attracting and catering for people from a wide range of ages and backgrounds, abilities and interests. First formed in 1922, the society has grown to over 1,000 members. Actually, I think it's close to 2,000 now. Its activities are coordinated by a council of elected office bearers, section directors and ordinary councillors. The ASV has weekly activities at our two metropolitan locations, the Morley Community Village and the Melbourne Observatory. We host monthly Astro Talks, which is coming up this Wednesday. The next Wednesday, there's an Astro Talk at 8 o'clock at the Herbarium in the Melbourne Observatory. Those Astro Talks are also streamed on the ASV's YouTube channel and Facebook channel page. The Society's library is also located at the Melbourne Observatory and is open during our Astro Talks. For over 50 years, the ASV has played a major role in the care of buildings and facilities at the Melbourne Observatory. Our members conduct astronomy for the people gatherings, or the American term is sidewalk astronomy, throughout the year, bringing telescopes and astronomy to Melbourne's parks and schools. Please check the calendar on the ASV webpage. There's a tab under events. There's a tab called events. Under the events tab is where you'll find the calendar. And so check out the calendar for any up and coming events that might be of interest to you. You can rock and roll up to those events. It's a public thing. So the ASV is currently involved in a number of major projects. We are involved in the restoration of the Great Melbourne Telescope, which is still ongoing. We're envisaging around the year 2027 or so when that telescope will be finally moved into a location where the public can actually see it. But it will be ultimately heading towards back to its original house, astronomy house, or dwelling at the Melbourne Observatory in due course. And also currently working on the installation of a series of remote telescopes at the Dark Sky site in Heathcote, just north of Heathcote. These remote domes, there's about 3 of them, I think. They're already set up and going, and still some on-air testing, so to speak, is occurring. But members will be able to access these remote telescopes through a schedule of some sort. But they are now available to members. Quite a lot of effort's gone into organising these remote domes, remote access type domes. Thanks to a generous donation from a long-standing respected members, the Leon Mao Dark Sky site is located north of Melbourne and has a pristine night sky for deep sky observing. The ASV has a 25-inch telescope there, a 40-inch telescope, and a wheelchair-accessible 16-inch telescope at the Leon Mao Dark Sky site, and makes use of the existing telescopes at the Melbourne Observatory during some section meetings and our members' nights held once a month at the observatory. There's also a fully steerable radio telescope at the ASV website, ASV Dark Sky site. It's called the Leon Mao Radio Telescope, Radio Observatory, forgetting all of a sudden there, LMRO, Leon Mao Radio Observatory. It's also located at the Dark Sky site, LMDSS, and it's a 8.5 metre, 30-foot Kennedy dish, which is fully steerable, and you can access involvement with that section through involvement with the radio astronomy section. There's also an annual yearbook supplied to members, as well as a bi-monthly newsletter. For those watching the video side, if you haven't seen it before, this is the ASV's yearbook. I'm not with it today, I can see that. The ASV yearbook, this is the 2024 one. It's quite a decent publication, and it's definitely worth joining the membership just for this bunch of information there, which works mostly for optical astronomers, but as you can quickly see, if I flim through the pages, you can get a bit of an idea of what's in there. So that's the yearbook, and then this is the Crux newsletter, bi-monthly Crux newsletter, which comes out bi-monthly. So so become a member of the ASV, and you'll get these additional things. The ASV logo, which I always have to mention, looks a bit like that, and of course it sports the Crux, the Southern Cross, and the pointers, and we have a motto which is in Latin, but I won't try and pronounce the Latin because I'm pretty useless at Latin, but it translates as "This way to the stars." The ASV is governed by a set of rules which should be read before applying for membership. Any person or organisation with an interest in astronomy may apply for membership of the Society. If you go to the website at www.asv.org.au, all will be revealed there. Joining the ASV is fairly simple, and it's all done by PayPal these days, and once you've signed on, you'll receive a members pack in the mail, which will explain everything else that you need to know about accessing the various sections, and how to access the ASV's Dark Sky site up at north of Heathcote. And for those also that aren't aware, there are currently about 18 sections, I think, that make up the ASV right now. You've got the astrophotography section, the club section, comet and meteor section, computing section, cosmology and astrophysics, deep sky, historical section, instrument making, juniors, lunar and planetary, new astronomers group, radio astronomy, solar astronomy, and space exploration. So again, if any of those sections sound of interest to you, just go to the ASV website, look under the sections tab, and all those individual sections that I just read out have an individual web page, and there'll be contact details for the section lead or director that you contact if you wish to ask if you can, for a night sitting on one of their meetings and see if it's of interest to you. And then, of course, they'll talk to you about becoming a member as well. Alright, so that's the ASV. It's 16 past the hour already. How quick that first 15 minutes has gone. I'll just check my my email, see if anything's come in. We've got an email from Stephen, VK3 SPX. He says 80 metres is a good signal, 10 over 9. Missing the other 200 watts. Right. Yes, I don't think it's the full 200 watts, just making sure that I don't interfere with the modem. Anyway, yeah, so anybody wishing to send a signal report, vk3ekh@gmail.com, vk3ekh@gmail.com. And a quick look at Discord. I can see that Andrew VK3KIS is there. G'day Andrew. G'day Mike VK1LO, and Steve, Mr. SPX, and our resident Mount Burnett Observatory astronomer, David VK3KDM. G'day David. Alright, let's get into it before the night runs on. Sky Notes, presented by Tanya Hill. Well, at least on behalf of her. Actually, I've got a picture of Tanya. So for those that don't know what Tanya Hill looks like, the current Sky Notes actually sports a picture of her, and I've just got it here. There it is. This is Mrs. Tanya Hill, and so I've had a chance to meet her some time ago at the one of the meetings of the Astronomical Society monthly meeting. She was there. Actually, she was actually doing a presentation there. So there it is. All right, now getting into the Sky Notes quickly. Trying not to sneeze again. Tanya's written here about finding exoplanets, a new approach. She says here that a new technique announced just last month may enable discovery of harder to detect exoplanets. That's exactly what she's written here. In simulations, it was able to identify and separate the light of a planet from the glare of its parent star. To date, among several methods used to find exoplanets, two have proven very successful in detecting almost 6,000 planets. Radial velocity analysis infers the presence of a planet by its effect on a star's movement towards or away from Earth, which subtly shifts in observed light wavelengths. And the transit method relies on changes in a star's brightness as a planet passes in front, briefly reducing the total light received by the telescope. Repeated detections using such methods are needed to establish the existence of an orbiting planet. And recently, direct detection of light from an exoplanet has added more, but the problem remains that many exoplanets thought to exist are still too faint to see or detect. The new approach lowers the detection threshold, it seems. Using a mask or a coronagraph can block out the intense light of the star to reveal much fainter bodies in orbit. This is how our sun's faint corona has been studied. But at the extremely faint levels, coronagraphs are plagued by light interference, causing diffraction that obscures vital details. However, an Arizona University team has developed a new approach using star masking combined with a two-step spatial method sorting process to reveal fainter planetary signs. And there's kind of a graph here of this. So, excuse me, Tanya, while I go to this little graph. There it is. Just bring that up. Okay, this is what they're referring to. The new technique. Just seeing where I was. Yep. The new technique may also prove useful in analysing magnetic or gravitational fields and in medical imaging and optical communications. So this graph that's on the screen right now, in this schematic, the raw image at left of a star potential planet passes through telescope optics. At center, the star is blocked out and the color or wavelengths of a potential planet are processed using mode sensors to overcome interference and diffraction to reveal the planet at the right. That's how it works. So she provides a couple of links on the on the SkyNotes website to learn more about the physics world. Coronagraph pushes exoplanet discovery, and the La Cumbres Observatory and exoplanets is the couple of links that she supplies. All right, now let me go to. She's about to carry on about the solstice. There is a video that she's got here. I think this is this one. I'll just run this. I don't think there's any audio. I won't worry about the audio, but I'll just loop it while I read out what she's got here in SkyNotes. Is that running? Yes, it is. Okay, winter solstice comes around again. The mid-year solstices for 2025 fall on the 21st of this month. Summer solstice for the northern hemisphere and winter solstice for the southern hemisphere. On that day, in the south, the sun rises and sets at its most northerly points on the horizon. Its path is the lowest of the year, giving us our shortest day, and its warming rays arrive at their shallowest angle, giving the least energy per square meter, and we are in the depths of winter if we aren't already. Solstice comes from the Latin sol, or sun, and sisteris, which is stand still. At the winter solstice, the sun is said to briefly pause at its northernmost extreme and then begins its daily southward rising and setting, with its path lengthening and days becoming longer until we reach the spring equinox, which is halfway to summer. This daily shift and the solstices and equinoxes results from the Earth's rotational axis being at a fixed angle or tilt of 23.5 degrees in relation to its orbit around the Sun. What you're seeing on the screen right now is a NASA visualization which shows how the Earth's tilt leans the southern hemisphere away from the sun in winter and the northern hemisphere towards the sun for its summer. Earth and sun are not to scale, of course, and at NASA solstice animations, solstices can be run for either hemisphere with or without labels. As she says here. And of course there's several other links that she adds to the Sky Notes to find out more about the solstices information. Alright, sunrise times, sunset and sunrise times for Melbourne. Sunday the 1st of June we had the sunrise at 7:26 a.m. setting at 5:09 p.m. On Wednesday the 11th, sunrise will be at 7:32 a.m. setting at 5:07 p.m. Saturday the 21st, sunrise will be at 7:35 a.m. setting at 5:08 p.m. and by the end of the month, on Monday the 30th, sunrise will be at 7:36 setting at 5:11 p.m. Okay, moon phases. First quarter is scheduled for Tuesday the 3rd. There's a full moon scheduled for Wednesday the 11th, and there's a third quarter phase on Thursday the 19th, and a new moon on Wednesday the 25th of June. Moon distances. Okay, there's a lunar perigee closest to the Earth is on Monday the 23rd at 363,178 kilometers. And then the lunar apogee furthest from the Earth is on Saturday the 7th, which is tomorrow, at 405,554 kilometers. And I've still got that animation running, haven't I? Okay, let's just cut that back to my camera. And I'll go to this shot here. Alright, continuing on with the Sky Notes. Planets. Mercury has moved from behind the Sun, but is not yet visible at night time. So it's not a nighttime object at the moment. Venus, as the morning star, can be seen from 3:40 a.m. shining brightly in the east before finally fading in the northeast by dawn. And sure enough, you can see Venus absolutely bright as in the morning. Mars is still an evening object and can be seen in the north at twilight around 6 p.m. before setting by 10:15 p.m. Jupiter is not visible this month as a nighttime object, as it is about to pass behind the Sun for its solar conjunction. Saturn has returned from its solar conjunction and can be seen from around 1 a.m. In the north before slipping from sight in the northwest in the early dawn light. Meteors. There are two minor meteor showers this month. The Aretid meteor shower in the constellation of Aries, which is occurring through to June 24, but peaks on June 11. From Melbourne, the shower is likely best seen just before dawn. Although low in number, less than 10 an hour, they can often be spectacular and bright, with many displaying a yellow-orange colour. The Boötid meteor shower in the constellation of Bootes appears late in June and into early July. The best time to see meteors is after midnight, with no moon in the night sky, of course. All right. Stars and constellations. If we turn our chair to the west, although Orion has disappeared below the western horizon, but his two dogs, Kansas Major with the star Sirius low in the west, and Kansas Minor with the star Procyon low in the northwest, are still both in our skies. If we turn to the north, Leo the Lion is still visible in the northwest with the bright star Regulus. Look for a large hook of stars or an inverted question mark to locate his curving mane and shoulders. You have to have a bit of imagination here. In the east, Scorpius is the southeast this month, and with the red giant star Antares as the middle of three stars that form the Scorpion's body. During winter, the Centaur Archer Sagittarius suits below the Scorpion with its bow and arrow, the famous teapot asterism. In the south, high in the southeast, is Crux, or the Southern Cross with the pointers, Alpha and Beta Centauri. Lower down, in darker skies, the two neighbouring galaxies, the large and small clouds of Magellan, can be seen as small isolated patches in the southwest. From our southern latitude, they are easily seen every night. In dark locations, the broad band of the Milky Way's billions of stars, numerous interstellar dust clouds, stretches across the sky from horizon to horizon, while some foreground stars in our local region of the galaxy can be seen. The dark dust clouds obscure our view further into the galaxy, since our eyes and optical telescopes see in only the visible part of the spectrum. The International Space Station orbits every 90 minutes at an average distance of 400 kilometres and appearing like a bright star moving slowly across the night sky. And here are some of the brightest passes expected this month over Melbourne. On the morning of Wednesday the 4th, which has been and gone, there was a passing at 6:15 a.m. to 6:20 a.m. On Thursday the 5th, been and gone, there was a passing at almost 5:30 in the morning to 5:32. On the evening of Friday the 13th, there's a passing at 6:52 p.m, starting at 6:52 p.m. to 6:55, coming in from the northwest to the north. And also on Monday the 16th of June, there's a passing at 6:03 p.m. to 6:09 p.m. west-northwest to southeast. If you go to the Heavens Above website, the Heavens Above website will give you more predictions and accurate accounts of when to be able to see the International Space Station at other times. And also anything else that's in the sky, any other celestial objects that are viewable, including amateur satellites. Okay, very quickly. On this day, I won't read all the dates here, but on this day, on the 1st of June 2002, the Czech Republic becomes the first country to ban light pollution. 2002. On the 2nd of June 1966, Surveyor 1 lands on the moon as first probe to land on another body. On the 3rd of June 1965, Ed White takes America's first spacewalk as part of the Gemini 4 program. On the 6th of June 1971, Soyuz 2 USSR carries the first people to a space station, Soyuz 1. On the 7th of June 1879, Johann Volt proves with parallax that the dwarf star Proxima Centauri is the same distance as Alpha Centauri binary. Good grief. On the 8th of June 2004, a transit of Venus is observed, the first in 122 years. It was in 2004. On the 9th of June 1986, Rogers' report on Space Shuttle Challenger explosion reveals solid rocket booster fault and a series management and safety problems with the US program. 1986. On the 10th of June 2003, launch of Mars exploration rover Spirit, which lands in 2004 and exceeds the expectations operating to 2010. That's the Mars exploration rover Spirit. On the 13th of June 1983, Pioneer 10 becomes the first object to travel beyond the planets of the solar system. And one more date, on the 13th of June 2010, the Hayabusa Japan craft returns the first asteroid samples back to Earth. Alright, the other dates I'll leave till later on, next week perhaps. You're tuned to ASV Radio, VK3 Echo Kilo Hotel, the official station of the Astronomical Society of Victoria, with the regular Friday night broadcast. Alright, and where's this picture? There's a picture here somewhere. There it is. Courtesy of astronomy.com. When was the last supernova seen in the Milky Way, is a question asked by a Judy Pierce in Texas. And SN 1987A occurred in the Large Magellanic Cloud, not the Milky Way. The Milky Way's youngest known supernova remnant is called G 1.9 plus 0.3. It says here that astronomers say our galaxy hasn't seen a supernova in 400 years. Why don't they count the 1987 supernova then? The 1987 supernova, SN 1987A, occurred in the Large Magellanic Cloud, LMC, not the Milky Way. The LMC is a small satellite of the Milky Way, but astronomers still consider it to be outside our galaxy. The 400-year figure refers to visual observations of supernovae in the Milky Way galaxy itself. Astronomers know other supernovae have occurred in the Milky Way since 1604, when Johannes Kepler observed one. But once scientists account for all known remnants and their ages, the Milky Way's supernova rate still seems low, or lower than that of our spiral galaxies, of other spiral galaxies. Astronomers suspect they have either misidentified or overlooked some remnants. Of course, just because we don't see a supernova doesn't mean they aren't occurring. Dust in our galaxy's disk prevents a lot of the light from reaching us. Infrared and radio wavelengths can penetrate this dust and reveal a few remnants. Then astronomers can watch how fast the remnants expand and figure out how old they are. Supernova remnant Cassiopeia A, the brightest celestial radio source beyond the solar system, is only about 300 years old. The only recorded sighting was by John Flamsteed on August 16, 1680, when he catalogued a star in the remnant's position. The Milky Way's youngest known supernova remnant is a radio source called G 1.9 plus 0.3. The remnant, which lies 27,700 light-years away, is only about 140 years old. This means that the supernova light swept over Earth about 140 years ago, but it took 26,000 years for the light from the blast to actually reach us. Radio astronomers using the VLA in New Mexico found that G 1.9 plus 0.3 grew by 16% between 1985 and 2008. That corresponds to an expansion velocity of 30 million miles per hour, or 48 million kilometers an hour, or about 5% of light speed. Because it's so young, G 1.9 plus 03 is still getting hotter and brightening at radio frequencies. Supernova remnants usually glow thanks to the interstellar gas heated by the explosion's expanding shockwave, but astronomers say most of the energy G1.9 plus 0.3 radiates arises from the debris of the exploded star. And that picture that's on the screen there is the supernova 1987A. At the centre, you can just make it out in the centre. There's two little circles and a little bright circle in the middle. This is SN 1987A. Is one of the most well documented supernovae in history. However, it did not occur in the Milky Way, but in the Large Magellanic Cloud, some 163,000 light years away. So there it is. It would have been nice to have been looking up at the sky in 1987 and seeing that happen. You're tuned to ASV Radio VK3 EKH, the official station of the Astronomical Society of Victoria, with a regular Friday night broadcast. All right, now you're going to have to, if you're sick and tired of hearing things about Mr. Trump, there's a couple of articles here, courtesy of astronomy.com, which talks about what Trump is doing to try and stifle the activity of NASA. This is not a very big article, but anyway, very briefly, let's just check my email for a second. Andrew is checking in. G'day, Andrew. Oh, it's Mr. KIS, no doubt. Okay, the move, reportedly motivated by Isaacman's past support of Democratic politicians, leaves NASA leaderless amid massive cuts in its science budget. Dear, this is really scary stuff for our space exploration program. This is Mr. Isaacman that this article is referring to. Oh, my nose is playing up. Okay, the Trump administration announced Saturday, May 31, that it would withdraw the nomination of the entrepreneur and private astronaut Jared Isaacman for NASA administrator. The move came just days before the Senate was scheduled to vote for or on his nomination, where he was widely expected to be confirmed. The Senate Committee on Commencing Science and Transportation had advanced his nomination on April 30 by a vote of 19-9 with a bipartisan support. The administrator of NASA will help lead humanity into space and execute President Trump's bold mission of planting the American flag on the planet Mars. Liz Houston, a spokesperson for the White House, which first reported the withdrawal, it's essential that the next leader of NASA is a complete alignment with President Trump's America's First agenda, and a replacement will be announced directly by President Trump soon. So the White House did not publicly give a reason for this reversal, but according to the New York Times, President Trump had concerns about Isaacman's political loyalty. It's always the way. The Times reported that Trump was informed of Isaacman's donations to Democrats in the past two campaign cycles, and as it will likely take months to confirm a new nominee, the move leaves NASA without a leader at a time of agency's turmoil, with its science division facing massive cuts in President Trump's proposed 2026 budget. The President's budget request, announced May 2 and released in more detailed form yesterday, would slash funding for NASA science nearly in half, from $7.3 billion to $3.9 billion, cancelling or closing out dozens of missions and scientific initiatives. Scientists and advocacy groups have said such cuts would have dire consequences for US science. The Planetary Society warned of a dark age, and an extinction level event in response to prior reports of Trump's budget. In a May 2 statement, the American Astronomical Society said that the administration's proposed cuts to science funding at NASA, the National Science Foundation, and the Department of Energy will result in a loss of America's leadership in science. Several members of Congress, which controls appropriations, have vowed to fight the reductions. Isaacman had faced scrutiny for his ties to Elon Musk, whose 130-day stint as a special government employee working with the US Dodge office recently concluded, and SpaceX, which holds key contracts with NASA, including delivering a Starship-based lunar lander for the crewed Artemis 3 mission. Isaacman served as a commander of 2 private spaceflight missions launched on SpaceX rockets, including the Polaris Dawn, where he became the first private astronaut to perform a spacewalk. During Isaacman's confirmation hearing, he was pressed by Senator Ed Markey about whether Musk was physically present when Isaacman met with Trump in late 2024. Isaacman declined repeated opportunities to deny that Musk was in the room. All this is really heating up, isn't it? But Isaacman was also seen as someone who might help NASA restore some of the funding and cuts proposed by the president's budget request. And in written responses to questions from senators following his confirmation hearing, Isaacman said a 50% reduction of NASA's science budget does not appear to be an optimal outcome, and that it would advocate for strong investment in science or space science for securing as much funding as government can reasonably allocate. He also reiterated his support for the Chandra X-ray Space Telescope, which would be closed out under the 2026 President's budget. So things are heating up over there, aren't they, one way or another? And then, of course, now we segue into another Trump thing. Let me just change the image here to guess who. By the way, I should mention, I don't know whether you people will remember, anybody listening will remember, but I think I said on air back in the beginning of the year that I said, I guarantee you Musk will fall out with Trump by the end of the year, and there it is, it's happened. All right, now briefly in this article, oh dear, here's how Trump's Golden Dome would work and why some call it a fantasy, courtesy of Astronomical. If the successful space-based missile defense system would protect the United States from advanced threats, but critics say it's upending international norms about peaceful use of space. On May 20, 2025, President Trump announced plans to construct a Golden Dome, a multi-billion-dollar missile defense system that would utilize space-based weapons and satellites to intercept ballistic attacks against the United States. This announcement stems from Trump's Jan 27 executive order titled Iron Dome for America. Inspired by Israel's Iron Dome and President Ronald Reagan's Strategic Defense Initiative, Trump's executive order declared his commitment to deploying and maintaining a next-generation missile defense shield. For some, this initiative marks a significant shift from the long-standing principle that space should be used for peaceful purposes. A vision of this principle was enshrined in the 1967 Outer Space Treaty, which banned signatories from placing nuclear weapons or other weapons of mass destruction in space, and designated celestial bodies as a domain of exclusively peaceful use. However, the treaty does not prohibit all military activities in Earth orbit, including conventional weapons systems like the Golden Dome. Still, the Golden Dome is viewed by many analysts as an escalation in the militarization of space. Trump's Golden Dome will be a missile defense shield utilizing a constellation of satellites and space-based weapons to intercept ballistic missile attacks against the states. In his May 20 announcement, Trump said that his administration had chosen an architecture for the program and that the system would be operational within 3 years, before the end of his second term. Once fully constructed, the Golden Dome will be capable of intercepting missiles even if they are launched from the other side of the world. And if they are launched from space, and will have the best system ever built, Trump said, as reported by the Washington Post in the Oval Office. At the same briefing, Defense Secretary Pete Hegseth described the project as a game changer. The system is designed to counter increasingly sophisticated threats from countries such as Russia, China, North Korea and Iran. According to the Pentagon, these nations have developed advanced long-range weapons, including ballistic, hypersonic and cruise missiles capable of striking the United States with conventional nuclear warheads. Yeah, I won't go all through all that. There's a few more paragraphs. Suffice to say that all the funding that's going on in this area is taking it away from other potentially good things that could be happening. If you want to read the rest of that article, it's astronomy.com. It's under the news tab, and look for the title, Here's How Trump's Golden Dome Would Work and Why Some Call It a Fantasy. So, yes, things are afoot over there, aren't they? Alright, let me go back to camera 1 and get back to some astronomical articles. This one, let me see, where am I? Looking for VMix again. Where am I? Sorry, just getting myself keyed up. I've just got a few more articles here, keeping an eye on the time. Alright. This is interesting. The James Webb Space Telescope gazes into the distant past through gravitational lens. The James Webb Space Telescope takes a closer look at distant galaxy cluster Abell S1063, which acts like a cosmic lens. And this is what is pictured. This is a really amazing photograph. If I can just find it. There it is. Get rid of Trump. Oh, my nose is playing up. Okay. Testing 1, 2, 3. In this picture, Abell S1063 is the tight collection of galaxies in the center of this image. Around it are streaks of light, which are each representing a more distant galaxy whose image is being gravitationally lensed by Abell S1063. Pardon me. The James Webb Space Telescope has captured a breathtaking new deep field image of the galaxy cluster Abell S1063, surpassing Hubble's previous view in both depth and detail. Abell S1063, located 4.5 billion light years away in the constellation of Grus, the Crane, Grus, Grus the Crane, acts as a gravitational lens. This massive cluster bends and focuses the light from galaxies lying far behind it, revealing some of the earliest galaxies in the universe. Hubble's 2016 deep field image of Abell S1063 first explored the cluster's gravitational lensing effect, exposing warped arcs of light, distant galaxies that would otherwise remain hidden to astronomers. Now, the James Webb Space Telescope's near-infrared camera, NICAM, brings these ancient galaxies into sharper focus, uncovering a large number of distant galaxies from early universe and other previously unseen features. This remarkable image didn't come easily, however. Unlike typical astronomical images, which already need long exposures, deep field images demand even more time, gathering as much light as possible to reveal the faintest objects in the universe. JWST's image of Abell S1063 combined 9 snapshots at different infrared wavelengths, totaling around 120 hours of observing time, JWST's deepest gaze yet on a single target. Studying these primordial galaxies provides a window into how the first structures of the universe formed. By peering through the magnifying glass of Abell S1063, astronomers hope to piece together the story of how the earliest galaxies merged, evolved, and ultimately gave rise to galaxies like our own Milky Way. So yeah, that's a pretty stunning image. I reckon that's just amazing stuff when you can see things like that. You're tuned to ASV Radio, VK3 Echo Kilo Hotel, the official station of the Astronomical Society of Victoria. This article, courtesy of ScienceAlert.com, the end of the universe could come much sooner than we thought. Courtesy of Science Alert under the Physics tab. And there's a video here which I'll run but without any sound attached to it as I read this article. May 13. A new calculation of the end of the universe suggests that the end of all things will come a lot sooner than our previous calculations indicated. Once the Hawking-like radiation emitted by everything in the universe is taken into account, the functional end of the universe is a mere 10 to the 78 years hence. Okay, so humanity will well and truly be dead by then, sure, but it's not less than 10 to 100 years we thought the universe had. So the ultimate end of the universe comes much sooner than expected, says astrophysicist Hino Falk of Rebound University in the Netherlands. He says, but fortunately, it still takes a very long time, the things that they work on. The work is a direct follow-up on a 2023 paper in which Falk, Falcke, and his colleagues, Michael Wondrak and Walter Van whatever, found that black holes are not the only things in the universe that emit Hawking radiation. Rather, less dense objects could also undergo a gradual evaporation in the form of Hawking radiation or something like it. And this is where this YouTube thing plays. Let me see if I can just run that in the background while I'm talking. I'll just make sure there's no audio there. Alright. So this is, sorry, this is not the article. Sorry, go back to me for a sec. That's the wrong one. That's actually the next thing I was going to talk about. Where's this? Oh, here, this is it. Alright, this is this YouTube
He was
thing.
perhaps the greatest genius of our time.
Mute that. Alright, so while that's running, just listen to me talking. Yeah, so this is a YouTube video. It runs for, I don't know how long. If I go back to vMix I can find out. It's 11 minutes. It's a little complicated, and we go into it more detailed here. That's a link. If you need a refresher. Jeez, these articles. But the basic gist is that Hawking-like radiation, the spontaneous production of particles that fly off carrying some of the black hole's energy with them, can happen at less extreme in space-time curvatures. Traditionally, it was thought to require an event horizon, the point at which the gravitational pull of a black hole is so strong that even light speed is no longer sufficient to attain escape velocity. However, the team found in 2023 study that it could also occur around other ultra-dense or very massive objects. This means that the space warping around neutron stars and white dwarfs, as well as massive galaxy clusters, should also be able to facilitate evaporation according to the team's model. After a very long period that would lead to everything else in the universe eventually evaporating, just like black holes, Falk explained in his article 2023. This changes not only our understanding of Hawking radiation, but also our view of the universe and its future, it seems. Well, the obvious next question is, how long is that going to take? So the team knuckled down and crunched out a few numbers. White dwarfs, neutron stars and black holes will belong to the same family of objects. They are what's left of a star after it dies, the outer material is ejected and the core collapses into an ultra-dense object. A star up to around 8 times the mass of the Sun turns into a white dwarf, which has an upper mass limit of 1.4 suns. Massive stars between 8 and 10 solar masses produce neutron stars, with an upper mass limit of around 2.3 solar masses. Stars more massive than 30 solar masses become black holes. There are limits there too. They are not irrelevant right now, but you can read a little about it here if you like. That's another link. The denser an object is, the more extreme its gravitational field. Of the 3 objects, black holes are the most dense and white dwarfs the least. This means that white dwarfs would take the longest time to evaporate. The time it takes for a white dwarf to die is the yardstick by which the team measured the remaining lifespan of the universe. Because black holes have the highest density and therefore the strongest gravitational fields, the team expected that they would take the shortest time to evaporate. Well, they were sort of right, because it takes 10 to the 67 to 10 to the 68 years for a stellar mass black hole to whistle away to nothing. But surprisingly, it takes neutron stars about the same amount of time. There's a pretty interesting reason for this. Black holes have no surface. They reabsorb some of their own radiation, which inhibits the process. For an average white dwarf, the team calculated a lifespan of 10 to the 78 years, putting roughly the upper limit on the lifespan of regular matter in the universe. There are, however, things in the universe that would take longer than a white dwarf, assuming, of course, that no other fate befell them in the meantime. It would take the moon 10 to the 89 years to evaporate. A human body would take 10 to the 19 years. So even if we wanted to live forever, we might eventually run into an obstacle here. A supermassive black hole would take 10 to the 96 years, while the giant halo of dark matter that engulfs the galactic supercluster would take 10 to the 135 years. Even that is far shorter than the 10 to the 100 million year lifespan based on the previous estimated lifespan of a white dwarf remnant. Goodness me. Obviously none of this is really going to cause any problems, of course. Even if humanity does somehow become interstellar before the death of the Sun in 5 billion years, we'd have to then somehow continue existing for many years, or many times the current lifespan of the universe. What the team hopes is that their results will help us understand the universe a little better before we go, and that at least we may still have time for. Yeah. Alright, well that's the end of that article. I thought that would be a little bit more interesting. It's one of these things that's got a few embedded links, and it's a bit involved. All right, this is VK3EKH, and that video is still running there, isn't it? I'll have to catch up with that video a little later on because it does look a little bit interesting. So that's on YouTube, and looks like it has some value. All right, back to me. Now, just let me see if I can squeeze in this last article before we go into... Oh, yes, okay. All right, let me run this video that I was running before, which goes for about a minute. All right, it has been thought that the galaxy Andromeda will collide with the Milky Way in the future. But it seems that it might not crash into the Andromeda galaxy after all, it seems. As it stands, proclamations of impending demise of our galaxy seem greatly exaggerated. That's the conclusion scientists have reached after revisiting the possibility. What we thought was a foregone conclusion, the eventual clash of giants, a collision between the Milky Way and the Andromeda galaxy. Led by astrophysicist Till Slawler of the University of Helsinki, a team of scientists has calculated that in the next 10 billion years, the chance of collision between the two galaxies is very close to 50%. In other words, there is just as much of a chance of a collision as there is of the galaxies sailing right past each other like ships in the eternal cosmic night. We don't find the previous calculations very... I'm just seeing where this thing's finished. Is that video finished, is it? Okay, hang on a sec. Let me just run this here. Okay, this is an artist's impression of our two galaxies colliding sometime in the future. Just to finish this article off, the Milky Way Andromeda collision was predicted by scientists for years, occurring in an estimated time frame of about 4.5 billion years. The predicted fusion of two galaxies has been dubbed Milkomedia, and has been considered to be all but inevitable. The Milky Way and Andromeda are not, however, alone in the little corner of the cosmos. They belong to a small group of galaxies within a radius of about 5 million light-years in the Milky Way, known as the local group. The Milky Way and Andromeda are the largest members, but there are quite a few other objects hanging around out there that need to be taken into consideration when modelling the future. Swaller and his colleagues took the latest data from the Hubble and Geospace telescopes and the most recent mass estimates of the four most massive objects in the local group, the Milky Way, Andromeda, and the Triangulum Galaxy, M33, and the Large Magellanic Cloud. When they set about running simulations of the next 10 billion years, adding and removing galaxies to see how that changed the results, almost all of the astrophysics and actually all of the known previous work is focused on trying to understand the past, how we got there and why. There are good reasons for that, but they say here, I think it's also fascinating to think about the future. Swall explained. Initially, I was motivated to understand the potential impact of the wider cosmic environment of the Milky Way Andromeda encounter, but as we show, there is actually a lot of complexity and uncertainty even with the relatively simple 3 or 4 body systems. Their results showed that the previous M33 and LMC dramatically altered the probability of a collision between the Milky Way and Andromeda. When it is just the two large spiral galaxies, the merger occurred in slightly less than half the simulation runs. The addition of M33 increased the merger probability to 2 or 3. Taking M33 back out and adding LMC had the opposite effect, decreasing the probability to 1 in 3. When all 4 galaxies were present, the probability of merger between Milky Way and Andromeda within 10 billion years is slightly more than 50%. They say that we find that there are basically 2 types of outcomes. The Milky Way and Andromeda will either come close enough on the first encounter that dynamical friction between the two dark matter halos will drag the orbit into an eventual merger, which very likely happens before 10 billion years, or they do not come close enough, in which case dynamical friction is not effective and they can still orbit for a very long time thereafter. That 10 billion year time frame was chosen because it was well beyond the time frame in which the merger was predicted to occur. But the further you try to peer into the future, the more difficult it becomes to predict. That's because other factors that can't be predicted may come into play. The further forward you go, the more likely those factors are to appear. So finally, this is far from the final word on the matter. However, although we have access to some pretty great data now, ongoing observations and future instruments will be able to refine the measurements of motions and masses of the objects in the local group to inform more detailed simulations in the future. The main result of our work is that there is still significant uncertainty about the future evolution and eventual fate of our galaxy. Of course, as working astrophysicists, the best results are those that motivate future studies, and he says, I think our paper provides motivation both for comprehensive models and for more precise observations. So that's courtesy of sciencealert.com. Under the physics tab, you look for the Milky Way might not crash into Andromeda Galaxy after all. And of course that's the artist simulation of the two galaxies merging there on the screen. Alright, you're tuned to ASV Radio, VK3EKH. Let's just quickly go into spaceweather.com. Let me see, where are we? There we are. The solar wind is currently at a speed of 465.6 kilometers a second at a density of 1.87 protons per cubic centimeter. The disk of the sun currently looks like this, with just a few sunspots visible on the disk. As some of you might be aware, we had a fairly busy sun this week with lots of aurora activity going on. But currently the aurora looks like this. So there's not much happening as we speak. But earlier in the week to the middle of the week, that green ring that we see over Antarctica had a lot of red in it, and was extending up as far as Tasmania. So there were some incredible some incredible aurora being seen and photographed around the place, that is for sure. So the current sunspot number is at 92. The radio sun is currently 134 solar flux units. The coronal hole is fairly obvious at the moment. If we can just bring up that image, please, producer. There he is. That fairly big hole in the surface of the sun there, where a lot of charged particles is being emitted, and the KP index, if I can just find that quickly, the planetary K index is 2.33. The 24-hour max is 2.67, considered quiet. And basically, space weather says a glancing blow CME. A CME that left the sun 3 days ago, when a magnetic filament erupted near the sun's equator, could glaze Earth on June the 7th. NOAA forecasters say that the glancing blow could spark G1 class geomagnetic storms. And that's about it. There's not much else to report there on spaceweather.com. Apart from the near-Earth asteroids, as of June 6, 2025, there were 2,349 potentially hazardous asteroids. But none of those asteroids are on a collision course, of course. Alright, I think that's where I'll finish up tonight at 11 minutes past the hour. I think I've done very good. Jeez. Alright. You're tuned to ASV Radio VK3EKH. Let me just check my email. That's Andrew checking in. Yep. All right. Let me just check our... And Andrew is still there. Steve is still there. David is still there. Okay. So, all right. Let's go to the radio to see if any stations wish to check in tonight. So this is VK3EKH, having a quick listen on 3541 kilohertz for any stations wishing to check in. Hang on, there we go. Where's the volume? Try again. Go ahead.
VK3 AOV. VK3 SPS.
Alright, we've got VK3AOB, g'day Britt, VK3SBX, g'day Steve, anybody else wishing to report in?
VK3 Charlie Alpha Hotel, check-in only.
Thanks Andrew. Who was the other station just then? There was another check-in. Aha, VK3EH, alright. I think you said you were just checking in. All right, no worries. Any other stations? Alrighty then. Thanks, guys. All right, across to you there, Brett. VK3AOB, VK3EKH.
Good evening. How are you going? here on the laptop. And I've also got your page up. So, yeah, very good. As usual, a good little session, and well done. Very professional. I was going to say, the 21st is this month, shortest day of the year, so we're now studying. It won't be long before it's spring. That's the good thing about winter. It's at least it starts and it always ends, and we go back to better weather. But anyway, nothing much else to add, so I'll hand it back to you, and I shall listen to until the end. Back to you.
Yeah, no worries, Britt, good on you. VK3AOB, VK3EKH, thank you for the kind remarks. I was struggling a little bit tonight, that is for sure. My nose was playing up, and I was in my left ear. I could hear strange modulations as I spoke, which was really putting me off, to be honest. But that's just an excuse, so just ignore that. There's normally a swag of pages I have opened up at the top of the screen here, but I've really got a minimal number tonight. The ASV homepage, Sky Notes, then there's 1, 2, 3, 4, 5, 6 articles. Normally I have more, and I just sort of choose between them, see if I can squeeze it in before the hour's up. And I still wanted to get that last article about Andromeda squeezed in, but unfortunately it took it over the 60 minutes. Not that I have to stick to the 60 minutes. It's just something I try to do, keep it within 60 minutes. But if I spill over 60 minutes, then that's just something I do. I don't have a clock to worry about. There's no time frame for what I do here on a Friday night. So it's just a matter of making sure that I don't become boring. All right, thanks, Brett. I thought Steve might have been there tonight, Mr. HK, but maybe he's gone to sleep while listening to me. That wouldn't be surprised. All right, thanks, Brett. Good signal from you too, by the way. Nice and clear, and 15 to 20 over 9. I think the band's a little quiet tonight. All right, across to Steve. VK3SBX, VK3EKH. Oops, wrong button. I agree. Yeah, no worries, Steve. VK3SBX, VK3EKH. Your signal tonight is actually quite weak. I don't know whether you've done anything there, or maybe you're running QRP. But I'm a bit surprised. I was just struggling a little bit to hear what you were saying. I got the gist of what you were saying, but you were surprisingly weak tonight. Now, I think that's just the conditions, just the band conditions. On the 1st of June 2002, the Czech Republic becomes the first country to ban light pollution. Wow. Yeah. I know there are places around in different countries where they do focus on light pollution and use special street lighting that focuses the light down and that doesn't have stray light. Where I live here in Narre Warren South, we're right on the intersection here, a T intersection, which is using LED lighting, and there's about 2, 4, 6, 8, 10, 12, let's say about 12 LED lights that really do illuminate the intersection out here. Fortunately, where my dome is, it's in the darkest part on the property, so there's actually quite a number of trees that block a lot of that light, but there are still some bright sources of light that do just sit there, and I'm actually going to request. I'm going to write off a letter or email Vic Roads. I think Vic Roads take care of these LED lights, but I'm going to request very, very politely, if it's possible, to place some sort of shroud over these lights to minimise the amount of stray light that's illuminating the properties around the place and focus the light down on the intersection where it needs to be. I don't think much will come from it, but I can always ask. I know the ASV has a section dealing with light pollution. I suspect they're still running, so I might notify the section director for the lighting pollution and see what he says about that. See what road I can go down to see if I can get any possibility of any success there. But it'd be interesting to see whether there is any chance of those lights out the front here being corrected. Just for good old me. I doubt it somehow. Anyway, or it is. That's excellent. All right, Andrew was a check-in. G'day, Andrew. Good to hear. Thanks for calling in. And I think it was Trevor, VK3 Echo Hotel, that called in as well. Is there any other stations wishing to check in before I disappear? VK3 EKH? Oh, wrong button. All right. On that note, this is VK3 Echo Kilo Hotel. I hope you listeners and stations that checked in found tonight's articles of interest. Certainly when we start talking about black holes and neutron stars and all these other fancy terms that are to describe these massive, amazing objects in the universe, it becomes a little bit difficult to understand the physics behind it. And I don't often pre-read these articles. I just hope that the descriptions that are used in these articles are easy enough to understand. But often the articles get very, very complexy very quickly, and I even in the back of my mind as I'm reading them out, in the back of my mind I'm thinking this is perhaps a little bit too much, and that's where I make the decision to stop reading the article and make reference to where you can if you want to read it for yourself. I'll tell you where it is, but I don't have the time, or I don't make the time to sit down and edit and reconstruct these articles that make it as minimal as possible. I just don't do that. So anyway, there it is. We do it every Friday. I always choose the articles from astronomy.com, from spacealert.com, from alert.com, space.com, all those .coms. Yeah. All right, enough of that gunge. This is VK3 EKH concluding for tonight's session. Thank you again for listening and watching on TV, and we'll be back next Friday to do it all again. Have a nice long weekend. Stay warm as much as possible. Sunday is going to be super cold. It's currently 10.7 degrees here, and the wind was up to a max. I think it reached about Yeah, I'm not sure how far it got. I think it was about 40 kilometres an hour. It gusted up to here just a few hours ago. So certainly got a bit windy in this location. This is VK3EKH with VK3CSJ on the microphone, concluding for tonight. Thank you for listening, and as I say, have a safe weekend, and we'll see you all next week. This is VK3EKH. Oh, wrong button. All right, so... yes, Steve, go ahead.
There is a Australian standard for light pollution, which you might be worthwhile looking out. I dare say Big Bros are probably aware of it, but a lot of other commercial organisations, I mean, just most people ignore it. But it'd be worth just checking out over the last about this month. Anyway, just thought I'd just pop in and mention that
your signal's just a bit weak. You were referring to the ASV's light section, yeah?
Negative. There's an Australian standard on light pollution.
Oh.
It'd be worth your while looking it up.
Okay, got it. No worries. All right, we'll look that up for sure. Australian standard on that. Okay. No worries. Have made a note of that for sure. Thanks, Steve. Good on you. All right. Thank you very much. This is VK3EKH. All right.
Everybody have a good weekend. 1 hour, 24 minutes and 51 seconds on the computer. I forgot that the 7300 had to record on the SD card, so I could have done that too. But anyway, there you go. All right. Talk to you next week.
Thanks, Brett. All right. Oh, dear. Oh, my nose. All right. To everybody who's been watching the video side of it, thank you for watching and putting up with the nonsense from here. And I'd be interested to know, there's someone I know by the name of Tuck Choi. If you've managed to watch tonight's broadcast, just let us know, just out of curiosity, to see whether you tuned into the YouTube channel or not. Because I don't see any remarks from you here, so you might not have had a chance to have viewed. I'm not sure what that was. Anyway, all right. We're out of here. I'm not going to prolong the agony. This is VK3EKH with VK3CSJ on the microphone, concluding for tonight and returning the repeater back to normal use, which is not a whole lot at this hour of the night. No, don't prolong the agony, Clint. There's nothing here I want to play that's of any interest. Or is there? Maybe I can run that Steve Hawking YouTube video that was going here somewhere. There it is. Let me cue that up. It only goes for 12 minutes. I haven't really checked this out, so I'm not really sure what's in it exactly. But I shall just reset it back to there, and I'll run this past that first. There we go. Okay. Now I'll pick it up and I'll put the audio on Discord. For those that are still listening to Discord, I'll make sure that you can hear what's happening on Discord. Hawking, there it is. Alright, so there'll be sound on Discord, and it's something to do with Stephen Hawking. It only goes for 12 minutes, and let's hope it plays okay. Right, VK3CSJ.
He was perhaps the greatest genius of our time. Stephen Hawking peered behind the curtain of reality and glimpsed the true workings of the universe. He inspired all of us to pursue our curiosity, no matter the obstacles. However, his true legacy is his work. He made profound contributions across physics, from quantum theory to cosmology. Our tribute is to bring you Stephen Hawking's most famous discovery. I'm Matt O'Dowd, this is Spacetime, and it's time for Hawking radiation. Soon after Einstein revealed his great general theory of relativity in 1915, physicists realized that it allowed for the possibility of catastrophic gravitational collapse. In places of extreme density, like the dead core of a massive star, space and time could be dragged inwards to create a hole in the universe, a boundary in space-time called an event horizon that could be entered, but from beyond which nothing could return. Once formed, there was nothing in theory or imagination that could bring material consumed back to the outside universe. These black holes should exist forever, only growing, never shrinking. Or so we thought, until 1974, when a young physicist named Stephen Hawking published a paper in Nature entitled Black Hole Explosions. In this, and in a follow-up 1975 paper, he attempted a new union of quantum mechanics and general relativity to show that black holes should not be so black after all. They should leak. They should emit what we now know as Hawking radiation. There's a popular description of how Hawking radiation works. It goes something like this. Empty space seethes with activity as pairs of virtual particles, matter and antimatter, spontaneously appear and then annihilate each other, briefly borrowing energy from the vacuum itself. But when this happens near a black hole, sometimes one of the pair will be swallowed by the event horizon, leaving the other free to escape and taking its stolen energy with it. That energy can't come from nothing, and so the black hole itself pays the debt by slowly leaking away its mass. This is a nice picture, but how accurate is it? In fact, if we follow the narrative of Hawking's original calculation, the story sounds rather different. We've come a long way over the past few months, building up the knowledge we'll need to follow that calculation. Rewatching some of those episodes, either now or after this video, will be helpful. But if you think you're ready, let's take a deep dive into the quantum field theory of curved space-time to glimpse the true nature of Hawking radiation. Actually, a quick QFT refresher can't hurt. Space is filled with quantum fields. They can oscillate with different frequencies, much like the many possible vibrational modes on a guitar string. A particle is like a note on the string, and just like a real guitar note, real particles tend to be comprised of many vibrational modes. Those underlying vibrational modes are still present in the absence of real particles. They fluctuate in energy due to quantum uncertainty, and those fluctuations give us what we think of as virtual particles. Now, don't take the existence of virtual particles too seriously. They're really just a tool for calculating the infinite ways in which a fluctuating quantum field can behave. One way that quantum fields are very different to guitar strings is that they can have both positive and negative frequencies. A negative frequency can be thought of as a mode that travels backwards in time and can be interpreted as corresponding to antimatter. Now, that's a whole level of weird all on its own, and we talk about it here. When a quantum field is in a vacuum state, there's a balance between positive and negative frequency modes, which you can crudely think of as a balance between virtual matter and antimatter particles. These all virtually annihilate or cancel out so that no real particles exist. This is all fine in flat space, but spatial curvature can mess with the balance of the underlying quantum field modes by introducing horizons. Horizons cut off access to certain modes of the quantum fields, disturbing the balance that defines the vacuum. Stephen Hawking knew that black holes, with their insane space-time curvature, would wreak havoc on quantum fields in their vicinity. But what would the effect be? To answer that properly, he would need a full union of general relativity and quantum mechanics, a theory of quantum gravity, a theory of everything. It didn't exist then, and it doesn't exist yet. Not to be deterred by the impossible, Hawking came up with an ingenious workaround. The narrative of Hawking's mathematics goes something like this. He imagined a single space-time path, a light-speed trajectory called a null geodesic. It extends from far in the past to far in the future. This is a perilous path. It passes through the location of a black hole in the instant before it forms. In fact, it is the very last trajectory to do so. It emerges barely ahead of the forming event horizon. Hawking imagined a simple quantum field tracing this path, a field that is in a perfect vacuum state before the formation of the black hole. But he found that the close shave with the black hole disturbs the fundamental vibrational modes that define the fluctuations of the vacuum. By the time this trajectory has found its way back out into flat space again, those fluctuations look like real particles. A distant future observer sees radiation coming from the black hole. Hawking's imaginary path from the distant past to the distant future was brilliant. It allowed him to compare the state of the vacuum in two regions of flat space far from the black hole, regions where the nature of vacuums, quantum fields and particles are perfectly well understood. But to understand the effect of the close encounter with the black hole, he required an uneasy marriage of quantum mechanics and general relativity. In the absence of a theory of quantum gravity, Hawking needed a hack. That hack was the Bogoliubov transformations. Say that 3 times fast. These can be used to approximate the effect of curved spacetime on quantum fields by smoothly connecting regions of flat space. They describe a sort of mixing of the positive and negative frequency vibrational modes that are caused by that curved space. The physical interpretation of this mixing via the Bogoliubov transformations is tricky. In fact, there isn't just one valid interpretation. Hawking's calculation talks about scattering. Certain modes of the quantum field are scattered or deflected by the gravitational field of the forming black hole. They are nudged off their narrow escape path and so are lost behind the forming event horizon. Meanwhile, other modes avoid scattering and continue unscathed. With the loss of certain fundamental modes, the vacuum state must be constructed from the remaining modes. That distorted vacuum looks like it's full of particles. The nature of the lost modes tells us what Hawking radiation should look like. Black holes tend to scatter modes with wavelengths similar to their own sizes. The quantum field that emerges is distorted in the same wavelength range, and so it produces wave packets. It produces particles that also have wavelengths about as large as the event horizon. So the more massive the black hole, the longer the wavelength of its radiation. Hawking calculated the frequency distribution of this radiation and found something incredible. It should look exactly like thermal radiation. Black holes should have a heat glow with an apparent temperature that depends on their mass. More directly, it's proportional to the surface area of the event horizon. Large black holes should appear cold, radiating excruciatingly slowly, but small black holes should appear hot, and the smallest should radiate explosively. Okay, so what about the whole picture of particle-antiparticle pairs being pulled apart by the event horizon? So Hawking's math describes splitting or mixing of these pure positive and negative frequency modes. It's fair to interpret this mixing as the promotion of what were once virtual particles into reality. And for the escaping modes, there exists a corresponding set of modes linked by quantum entanglement that are trapped behind the event horizon. We can interpret those as corresponding to the swallowed antiparticle partner. So the split matter-antimatter part of the picture is reasonable. But there are reasons to dismiss aspects of this picture. Firstly, this radiation is not localized. Remember that Hawking radiation has wavelengths the size of the event horizon, the size of the entire black hole? Well, these are the de Broglie wavelengths of created particles, and they tell us that there is an enormous quantum uncertainty in the location of these particles. Hawking radiation must appear to come from the global black hole, not from specific points on the event horizon. In fact, an observer in freefall through the horizon sees nothing. To them, space is locally flat. The vacuum should look like a vacuum. This radiation is visible only to distant observers. Well, there is one exception. When you turn on your jetpack and hover a fixed distance above the horizon, then you do see particles. You see Unruh radiation. We'll look at its relationship to Hawking radiation in the future. By the way, Hawking radiation is mostly going to be photons and other massless particles. To produce particles with mass, the energy of the radiation has to be high enough to cover the rest mass of the particle. So it's okay to interpret the narrative of Hawking's calculation as the splitting of entangled matter and antimatter pairs, even if it really is just a heuristic interpretation. It's the cause of the splitting that's hard to pin down. We can think about positive and negative frequency modes being mixed due to scattering, perhaps by the as yet undiscovered graviton. Other physicists have derived Hawking's result with very different seeming narratives. For example, in 2001, Parikh and Wilczek got the same thermal spectrum for Hawking radiation by thinking about particles escaping from beneath the event horizon through quantum tunneling. The common thread is quantum uncertainty. For example, uncertainty in position or momentum can lead to particle pairs that were once in the same location, or modes that were once on the same world line becoming separated by the event horizon. Alternatively, uncertainty in energy can lead to particle creation. Whichever way you interpret it, it's hard to avoid the conclusion that black holes emit particles. The fact that different derivations lead to exactly the same result, or that the radiation looks thermal, can't be by chance. It's hard to make Hawking radiation go away in the math, and believe me, Stephen Hawking himself tried. Ultimately, however, these calculations are all hacks, albeit utterly brilliant ones. Without a full quantum theory of gravity, the origin of Hawking radiation will remain mysterious. And there are other mysteries that we haven't touched on. For example, what happens to the particles or modes trapped by the black hole? How do they end up reducing the black hole's mass instead of increasing it? And then there's the famous information paradox, in which Hawking radiation appears to destroy what should be a conserved quantity, quantum information. We'll tackle all of these in future episodes. For now, we must conclude that black holes radiate and in doing so evaporate. The scariest monsters of general relativity are ultimately unravelled by the brilliant mind of Stephen Hawking and a mysterious quirk of quantum spacetime.
Right. Well, I hope you got something out of that. It's a whole different level of physics. Anyway, it's all very interesting stuff, and there it is. All right, we're out of here. This is VK3CSJ concluding transmissions for tonight. Thank you for watching and listening, and we shall see you all the Sunday morning with the WIA broadcast. Will be the next session that I do, 9 o'clock Sunday morning on 1825 kilohertz AM, and then at 10 o'clock, 10:30 on ATV, where we do it all again. So trying to find my test pattern here. There it is. So cheers for now, everyone. Take care and have a pleasant long weekend. Cheers. This is VK3CSJ.